Hello everyone. In the previous video, we built this function spiral matrix. Let's review what it does. We generate a matrix, a square matrix with all zeros, and we supply this matrix and the initial value spiral matrix. Let's run here. And as you can see, from the initial value, it arranges the numbers in a spiral order up to the final value. In this case, is 9. In this video, we are going to reverse this process. Basically, we will supply a matrix with zeros, a square matrix, and a final value. So let's check it. This again, a matrix with all zeros. And let's supply 9, the same here, the final value. And if we do this, as you can see, the output is the same, but we are going backwards. So basically, it's very clear what we have to do in this video. From the final value, we have to go backwards and we have to reduce y unity each step. But this case is trickier than the previous one. Let me show you why. Let's see some example with 4x4, 5x5, 6x6 and 7x7 matrix. Now, first question is, where is the initial value? And the initial value is always located at row 1, column 1. You can see, regardless of the size of the matrix. Now, why this is 3? Because in the previous case, the final value is equal to the number of row multiplied by the number of column. 3 by 3, 9, 4 by 4, 16, 5 by 5, 25, and so on. In this case, 7 by 7 is 49, but we set as a final value 51. 51 is 2 units to the right of 49, so this means that the initial value is not 1, but is 2 units to the right of 1, the 3. I said this because we will see this how we set this in the code later on. The other question now is, where is located the final value? And as you can see, this is a 3 by 3 final value is located in the row in the middle and column in the middle. But in the 4 by 4, the final value is here, it's 3 and 2. And in the 5 by 5, it's located at 3, 3. This is a 6 by 6, located at 4, 3. And 7 by 7 is located at 4, 4. So as you can see, the location of the final value changes based on the size of the matrix. But we can say something more because we can identify a pattern. Let's call the matrix with an odd number of rows and columns odd matrix, and the one with an even number of rows and columns even matrix. And as you can see here, 9 is located at 2, 2, and that is the middle row and middle column. 5 by 5, this is also odd, and it's located at 3, 3, and again, this is the middle row and the middle column. 7 by 7, as you see, it's located at 4, this is the row in the middle, and column 4 is the column in the middle. On the other hand, for an even matrix, you see that 16 is located at 4 divided by 2 plus 1. For the column, is located at 4 divided by 2. For 6 by 6, 6 divided by 2 is 3 plus 1 is 4. 6 divided by 2 is 3. So we will consider these two facts to locate the final value. Another point that we have to take in consideration is the rotation. Let's consider always the case when we start from 1. Here, if we start from the initial value here, the rotation is always the same, regardless the size of the matrix. If the matrix is odd or even, doesn't matter. We go from left to right, from top to bottom, from right to left, from bottom to top, and then we start again. And as you can see, this is for all the matrices. On the other hand, let's consider the rotation from the final value. Let's consider here we are in an odd matrix 25. We go one step from right to left, or one step from up down 23, and two steps from left to right, and two steps from down to up, and then we start again. But let's consider now the even matrix. We are here 36. In this case, we are going one step from left to right, one step from down to up, two steps from right to left, and two steps from up down, and then starts again. As you can see, the rotation changes based on the fact if the matrix is odd or even, and we have to take this in consideration. So let's see how we can do this. Okay, so we set a name for the function, in this case reverse underscore spiral underscore matrix, an operator, function, and the two arguments of the function, m, that is a square matrix, and the final value. Now, the first thing that the function does is to check that the matrix that we supply is a square matrix, because this code works only for square matrices. If the number of rows of the matrix, number of columns are different, the matrix is not a square matrix, and the function will stop. Will print this error message: the matrix must be square. If the matrix is square, the function continues. So the first thing is that we have to check if the matrix is odd or even. And we do that by checking the remainder. That is, we check the division between the number of rows of the matrix divided by 2. But this one will return the remainder. What does that mean? Let's suppose that we have a 4 by 4. The number of row 4 divided by 2 is 2, with the remainder is 0. If we have a 6 by 6, number of row is 6, 6 divided by 2 is 3, with remainder 0. If we have a 5 by 5, 5 divided by 2 is 2, with remainder 1. So in the case of an odd matrix, the remainder is different from 0. So if this n is equal to 0, and here if n double equality is equal to 0, and in the case of the even matrix. And this code here is for the even matrix. So let's check it. The first thing here is to set the final value. And in the case of an even matrix, we set number of row divided by 2 plus 1, and number of column divided by 2. And this is where we located the final value. Then we have to set the initial values. This one, these values, they control for the loop sequence. And this value here, we control for the fixed row and fixed column in the loop. I will explain in more details these values when we break down the function later on. Then we set the condition to stop the loop. As min equal to 1 plus the difference of the final value minus here the number of row of the matrix square. So here, when for the 7 by 7 we supplied 51 as a final value, here the minimum value is 3. Why? Because 1 plus 51 minus 7 square 49, so 51 minus 49 is 2, 1 plus 2 is 3. And This is where this tree is coming from. On the other hand, if we set 49 as final value, 49 minus 7 by 7, 49, this means that this is 0, and this would be 1, okay? Then we are summing the absolute value of the sequence that goes from the final value to S min. And then here, Sm, we are checking the sum of the absolute value of the entries of the matrix M. So now we are still outside the loop. So here, this value will be the value of the final value that we set. And from now on, the loop starts. Again, this is the loop for the even matrix. We have a while loop that starts here and ends here. And inside the loop, we have 4 loops to control for the 4 direction, from left to right, from down to up, from right to left, from up to down. And notice something, that here, after the from right to left loop, we check the sum. Basically, we are updating the SM object by checking the sum of the absolute value of the matrix. This is because now this M matrix will be filled up with these values here. And if Sm is equal to Sv, this is the condition to break the loop. So if Sm is less than Sv, we are continuing the loop. After the fourth loop, we are updating these values here. These are the values to control here for the sequence and control for the I row and j row. When Sm is equal to Sv, this breaks the loop, and the matrix with all the values will be returned. Okay? On the other hand, if n is different from 0, we are in the case of the odd matrix. And this is the code for the odd matrix. So basically here, we are setting the final value, and we are setting number of row minus 1 divided by 2 plus 1, number of columns minus 1 divided by 2 plus 1 to set the final value. Again, we set the initial values by taking consideration that this is an odd matrix. Okay, here the condition to stop the loop is the same. And now the loop starts here from while, and the loop ends here. Okay, now these are the 4 directions from right to left. In this case, we check here the sum of the absolute value, because we know that will be always from the right to left that we will break the loop here. So that's why we are going to check after this loop here, we are checking the sum. Now naturally this is the first loop, so this will be Sm will be not equal to Sv, will be less than Sv, so the loop continues here. But again, this will be clear when we break down the loop. And again, after the for loop, we updated the values, and the loop starts again from here, check the sum, continue, and so on. And when this is true, the loop breaks and return the function return the matrix with updated values. So let's run this code here. Let me remove, so we run again, remove spiral matrix, reverse spiral, and remove both. Let's run again. Okay, now let's test. We have 8 by 8. You can see final value 8 by 8 is 64. So well, let's check this one. You see we have an error. The matrix must be square. Why? Because we have supplied a 7 by 8 matrix. So this is not square, and this is the condition that we set here. Let's continue. Let's see another case here. This is always 8 by 8, but we are starting from a negative number. By then, starting from 100, and we end up at 1. Let's see this other case here, 10 by 10, but we are starting from 99, and we end up at 0. See this one, 10 by 10, but we are starting from 50, up at minus 49. Let's see the last example here. This is 5 by 5. We're starting from 10. So now, this is the example that we are going to break down. What do I mean with break down the function? As you can see here, we have only two objects. The M matrix, and this is the matrix with all zeros, as you can see here, and the function reverse spiral matrix. But we don't have the final value, we don't have any FL, SL, all these objects. Why? Because these objects are inside the body of the function. So now what we are going to do is take the content of the function and bring it out from the function. Okay? So let's see. Let's build this 5 by 5. Now, the first steps that we do is that we assign the final value. So to replicate this example, the final value here is 10. So we are building this object fp equal to 10. Okay, as you can see now, we have the object here. The first check to check the function. Okay, we know that this is a 5 by 5, so we are not checking where. So what we are doing here is checking n. So if the matrix is odd or even. So let's make this. You can see now n is equal to 1. So this means that we are in the case of the odd matrix. And now the code here is the code for the odd matrix. So you have to think that we are inside the function. Okay, so we are simulating what the function does. So here, number row minus 1 divided by 2 plus 1, number of columns minus 1 divided by 2 plus 1, this is the location of the final value. So if we run this code, you can see now we placed our final value. Now it's time to build these initial values here. Okay. These are for the loop. These are for the ing column. And again, this will be clear in a moment. I will explain in a moment. Now, the condition to fulfill to stop the loop. Now, fv is 10. So what does it mean? That this is 10 minus 5 square, because we have a 5 by 5 matrix, 25. So 10 minus 25 minus 15. So this means that S min is minus 14. You can see here the reverse spiral matrix 5 by 5, final value 10, and this value here is minus 14. This is what we set here. Now, let's continue. We are working here, we are summing the number in the sequence from FV to Smin. So from FV is final value is 10, Smin is minus 14. This is the sequence. But we are summing the absolute values. Why? Because if we sum this number here, you can see that 1 will be cancelled out by minus 1, 2 by minus 2. So for this reason, we are considering the absolute value. Okay? So we are summing all these values here. SV is this, 160. Now we are summing Sm, the sum of the value, the absolute value in the matrix. But now M, just one value, the final value, 10. So this means that Sm now is just 10, but this value will be updated in the loop. Okay? So now, after we have done this, the function starts the loop. We have a while loop and we have a for loop for direction. Now, we implement only the for loop for the direction because we will check manually when Sm is equal to Sv. This is what the while loop does, okay? So we are doing that manually. And now it's time to explain this FL, IFL. Basically, we are here, 10. We are moving from right to left, from right to left. So we have to move one step. FL is a sequence, it's just one step, and that step is 2. Let me print here. That step is 2. What is this 2? This 2 is the value of j. So for j, in this sequence, in this case the sequence is only one number, so for j, that is 2, we are implementing this code here. IFL here is 3. Why is 3? Because we are on this row here, and we want to update this value. This value is located at row 3, column 2. So what we are saying is that the value at row 3, column 2 is equal to the value at row 3, and this is 2 plus 1, column 3. So row 3, column 3 is this value, is 10. So basically, this one corresponds to this 10 minus 1. So when we run this code here, what we do is 10 minus 1, 9. We updated the value at row 3, column 2. Now, as I said, we check here the sum, and it's 19. So we still have a lot to go to reach 160. And then we go to the second direction, so second loop from up to down. So let's check now what is this sequence. This is only one number, and this is 4, because we have to move only one step, and this step is row. Now we're moving from up to down, so we're moving along the rows. So it's I for the row, and this is 4. What is JSL? 2. Why? Because we are in column 2. So we are saying the value at row 4, column 2 equal to the value at I minus 1. But now I is 4. So 4 minus 1 is 3. J underscore SL is 2. So we're saying that this value is equal to 9, because this code here corresponds to this value here, minus 1. So when we run this, as you can see, 9 minus 1 is 8. We updated this value here. Now we have to move from left to right. Now notice that we have to fill two values. The sequence here, if we check this sequence now, is 3 and 4. We have two values here. The beginning, j is 3. So basically j is 3. What is ITL? ITL is 4. So 4, 3. So this means that we are updating, we are actually overwriting this value here. So this value here is equal to this code here. This code corresponds to 8. Why? The row is fixed, but j is 3 minus 1 is 2. So I said I is fixed, j is 2. So it's 8 minus 1. Then we have another value in this case. The other value is 4. So we have here row 4 that is fixed, but now the column is 4. We're saying that row 4 column 4 is equal to row 4, and now j is 4, 4 minus 1 is 3, so we are saying that it's equal to this value that has been updated minus 1. Let's run. As you can see, we have 7 and 6. And then we have to go from down to up. The reasoning is the same. Now, this is the sequence. We have 3 and 2. We are going 3 and 2. And we are updating these values. Let's run this one. As you can see, we have 5 and 4. Now, we have to update all the values because this is the first time all these for loops they've run. Now we have to update this value. If we don't update these values here, the loop will be always the same. Count, if you remember, count is 0. So what we are doing here, we are saying count, we are updating by summing count plus 1. So now count, we check it, is 1. And we're checking this value for I and j, okay? And naturally we have to check here minus 1 or plus 1 depends on where we are located, okay? And now we have to start again from loop number 1. So let's go back to loop number 1. And as you can see now, count, as I said, is 1. So we updated this basically. And how do we update it? By extending 1 to the left and basically 1 to the right of 2. Remember at the beginning, the sequence was only one number, that number was 2. But now we extend it to 3, 2, and 1. But now also this has been updated. So at the beginning, if you remember, we were here and the row was 3. And now we updated and the row is 2. And as you can see, the sequence is this one, 3, 2, 1. Naturally, the reasoning is the same. We run this and we updated these values. Now we check again. And we are far from 160. So we have to run the other loops. And again, all these one, they have been updated. The sequence has been updated. So if we run this, you see, now from left, right, from left, right, we moved this. Then we have from down to up. And now, as you can see, we need to run the loop again because we have to fill these values here. But this means that we have to update again these values. Sorry. So remember, count 1 is 1, and now we have to update. So now count 1, 2. We also update these values here. And we have to start again from the loop number 1. Now, when we run this, as you can see, we completed the sequence from 10 to minus 14. What does that mean? That if now we check, remember SV is 160, but now SM is 160, and this is the condition to break the loop. This is the simulation of the function step by step. I hope that this is useful, and if you enjoyed this video, see you in the next one.